Thank you, Philip. So I would like to discuss with you some aspects of Sarnak's conjecture on Möbius orthogonality. So here is this conjecture. So it says that for each topological system of zero topological entropy, we see that the limit, which is written here, is equal to 0 for all continuous functions and for all x's. So let's start first with explanations. What's happening here? What is it all about? So first remark is that we are going to talk about uncorrelation of sequences. So by definition, all sequences are bounded, or quite often they will be bounded by 1. So when we want to talk about uncorrelation of sequences, so we have this psi n, eta n. So we want to see the following, that the mean of the product of these two sequences is close to the product of the means. But you can very quickly notice that if one of these sequences has the mean equal to 0, so then in fact uncorrelation of sequences ends up with this limit equal to 0. So in other words, what we are talking about here is an uncorrelation of the Möbius function with some sequences. Which sequences? Well, so we have a compact metric space X, and then we have a homeomorphism acting on that space. Then we consider all continuous functions. We take any point X, and we consider a continuous observable, which means look at the orbit and look at the values of your function f on the orbit. And these are your sequences. And what's important is that what we are going to consider here as dynamical systems, they are of zero topological entropy. Of course, I just recall that the mean of mu is equal to 0. So this is a statement which is equivalent to the prime number theorem. And to see that, certainly we will see that we face a difficult problem is that, well, we're not so far from Riemann hypothesis, because any quantitative cancellation of plus ones and minus ones let's say of that kind, it leads to, it's equivalent to Riemann hypothesis. So, okay, so the Möbius function already appeared, right? I just recall its definition. There will be also Liouville function, multiplicative function, very similar to the Möbius function. And we are going to talk about Chowla conjecture. So Chowla conjecture was formulated 60 years ago, and it is telling us that what we should expect from the Liouville function is that all the correlations of the Liouville functions are equal to 0. So I will concentrate on ergodic theory aspects of these two conjectures, Sarnak's conjecture and Chowla conjecture, and this will be the first part of my talk. It will take about 2/3 of the talk, and at the end of my talk, I would like to concentrate on some some recent results, which somehow will explain why, despite, the Sarnak's conjecture was formulated 15 years ago, it's still open. And so I would like to explain to you, a little bit, why is it so? And I would like to show you some present challenges. Okay, so I have to start with some basics of ergodic theory and well, and the theory of dynamical systems. So in ergodic theory, we consider measure-theoretic dynamical systems. So we have probability spaces and we have an action. So T is an almost everywhere bimeasurable bijection. So we have an evolution in that space which is given by T, and the only law which we consider is that, well, sets are somehow moving, but what we require is that the measure does not change. I may call this measure-theoretic dynamical systems simply automorphisms if all objects are clear. So of course, as often in mathematics, if we develop a theory, so we are interested in objects which are in indecomposable. So in ergodic theory, such objects are called ergodic. So we call it automorphism ergodic if it has no non-trivial invariant set. So in other words, if I have a set and somehow its preimage is almost everywhere the same, so then this set has to be trivial. It's either of measure 0 or of measure 1. So the idea is that if we have a set which is invariant, so then we can decompose our dynamics into two parts. But this is what we want to avoid. Given this automorphism T, we can consider the associated unitary operator acting on the L2 space. So because T is measure preserving, so this operator is unitary, the scalar product is preserved. This operator is often called the Koopman or the Koopman operator. And if it happens that the L2 space has an orthonormal basis consisting of eigenvectors of this unitary operator, so then we say that T has discrete spectrum. So a natural example of what we are talking about is just take an irrational rotation on the circle. Of course, it preserves Lebesgue measure, and it is not hard to see that this is an automorphism with discrete spectrum, because just consider characters of this group. You can see that these are eigenfunctions, and ergodicity is also proved using Fourier analysis. So ergodic theory is not so far from probability theory. And to see a relationship, let's just notice that if we have a measure-theoretic dynamical system and we take any measurable function, f, so then the process which we can associate to f, this process is stationary, which the stationarity means that, well, if you look at finite dimensional distributions, so that they don't change if we shift everything if we shift everything in time. So whenever we find f such that the process, this f composed with t to the n, is independent, and the smallest sigma algebra making the process measurable is the whole sigma algebra, then we say that we deal with a Bernoulli automorphism. The entropy will play an important role in this talk. So let me just recall basic of entropy theory of measure preserving actions. So I just recall that if we have a random variable and we assume that this random variable takes only finitely many values, so then the Shannon entropy of this variable is just given by this formula. So these Wi are just values taken by our random variable. If we have two random variables, and of course somehow we know the joint distribution of this vector, so then we can introduce conditional entropy and by this formula. And the conditional entropy is of course small, always is smaller than h of w, like here, but if there is equality, so then it means that these two variables, they have to be independent. Okay, so now we go back to stationary processes. So suppose that we have a stationary process. We assume again that this Z0 takes only finitely many values. So then we claim that this limit exists. So if you forget about this 1 over n and you consider this sequence, so the crucial observation is that this sequence, as a sequence of n, depending on n, it's subadditive, so that by a general property of subadditive sequences, the limit exists. And this limit is called the entropy of the process and denoted by h of underlined z. On the other hand, this quantity, the entropy of the process, can be computed by using conditional entropies. So, well, we introduced already conditional entropy, but in the case where W prime takes only it's just a random variable. Here you have infinitely many, but you should think that, well, take from 1 to n and then pass to the limit. It's clear that this sequence is monotone. So as I said, conditional entropy is always smaller than the entropy of this random variable. But if we have equality, so this is if and only if the whole process is an independent process. So we deal with this Bernoulli case. On the other side of the hill, we find processes whose entropy is equal to 0. Such processes are called deterministic. And the theorem about the deterministic processes is the following one, that Z is deterministic if and only if Z0 is measurable to the sigma algebra generated by Z1, Z2, etc. Usually we say that the presence is determined by the past, but I interchange the role of the future with the past. It leads to the same quantities. So now we are interested how to introduce the entropy of a measure-preserving dynamical system. So if the entropy is introduced in the following way, so this is called Kolmogorov-Sinai entropy. Simply we take all functions, all measurable functions, taking finitely many values. We look at the associated stationary processes. We know what is the entropy of these processes, and we take the soup. Okay, so for example, discrete spectrum automorphisms, namely those having this orthonormal basis consisting of eigenvectors, eigenfunctions. So these are examples of zero entropy dynamical systems. There are automorphisms. There are systems in which, for all non-trivial processes, the entropy is positive. So these are called Kolmogorov. And Kolmogorov automorphisms are automatically ergodic, and Bernoulli automorphisms finally are Kolmogorov. Okay, so this is ergodic theory. Now we need something simpler as for notions, namely topological dynamics notions. So what is a topological dynamical system? Well, we simply have X is a compact metric space and on which we have an action of a homeomorphism. So a rich source of topological dynamical systems is given by subshifts. So what is a subshift? Well, first we choose an alphabet. So we have a compact space, a compact set. So in our situations, often it will be just the situation that we take the unit disk and we take a compact subset of this unit disk. And then we consider the space of all two-sided sequences whose over the alphabet A. So that this is called this space A to the Z is called a full shift. I mean, on that space we have the natural action of shift by one position to the left. But so this is called a full subshift, the full shift. But if we take as a closed subset of the space of all two-sided sequences, which is also S invariant, so then we obtain what's called a subshift. Well, anyway, if we have a subshift, so then we can compute its topological entropy, and the topological entropy is computed in the following manner. So we fix N, we look at all two-sided sequences that belong to X, and we consider windows of length N, and we read all possible blocks of length N. Okay, so this is this number. I mean, this is the set B of N. We compute how many blocks we have, and then we are interested in the situation in which in answering the question whether this is exponential growth or it's not, or it's sub-exponential. So this limit exists again because this log is a subadditive sequence. So I'm not going to define topological entropy in a completely general setup. This will be sufficient for us. Well, anyway, but how to obtain a subshift? Well, to obtain a subshift, it's enough to have a point, one fixed sequence, two-sided sequence over the alphabet A, because then we can consider the orbit and we can take the closure of the orbit. Of course, there is this little inconvenience that usually we are going to play with arithmetic functions, and they are really one-sided. So we want to extend them to two-sided. We can do it, you know, just in a, I wrote here this possibility or a variant that we just take a symmetric version. So in particular, we have these two subshifts, Möbius subshift and the Liouville subshift. So Möbius subshift is just take the Möbius function, let's extend it symmetrically, and then treat it as a point in the space of all two-sided sequences of plus ones and minus ones and zeros, and take the closure of that. So, and the same story with the Liouville function, even though here the alphabet is just -1, 1. From topological dynamics, we can pass to ergodic theory. The question is how. And the idea is the following, that, okay, so I have this compact metric space X, so we can consider all probability Borel measures on X. And then this is a space, this is a symmetrizable space we considered with this weak star topology. I just recall that nu n is going to nu in this topology, if and only if, well, we see that integrals are converging as well one should expect. But on that space, but this is of course without any action on X. But now we have this homeomorphism T, which is defined on X, and then we can think, okay, but I would like to see that there are some invariant measures, invariant under T. So I can see that there are some, however, there are some little mistakes here, that the measure is denoted. Okay, so if I have an invariant measure, so then of course I have a measure-theoretic system automatically. And something to be remembered is that, so this set of invariant measures, it has a natural structure of an affine set. So we know what are convex combinations of measures which are T-invariant. They are still T-invariant. And what we are interested in is that what are the extremal points of this set. This is also closed. And that's something very basic in ergodic theories, that extremal points in this set are exactly ergodic measures. By ergodic measure, we understand that the corresponding dynamical system is ergodic. So of course, everything now, so this is something completely general, but the point is, do we have invariant measures? And to see that there are plenty of invariant measures, or at least there are some invariant measures, is the following construction. Look at so you take a point little x, you look at its orbit, and you create so-called empiric measures. So we take the initial part of the orbit, we give them the same measure 1 over n, and then so these measures on the left-hand side are not T-invariant, but when we pass to a limit, and remember that we are in a compact space, so we can pass to a limit, so we obtain a measure which has to be T-invariant. So the language which is used here is that, well, a point is generic for a certain measure if the whole sequence of empiric measures is converging to nu. That is, for all continuous functions, we see that we have this convergence. If the convergence takes place along a subsequence, then we speak about quasi-generic points. And of course, because of compactness, each point is quasi-generic for a measure. But remember that there are invariant measures for which there are no quasi-generic points. So those measures which can be somehow seen from these quasi-generic points, that these are called visible measures. So what we are interested in is that we have a compact metric space, we have a homeomorphism on that, and we want to see visible measures. We can repeat the same arguments using a different way of averaging. And this different way of averaging, for this talk, it will be just taking logarithmic averages. Okay, so we consider now this kind of empiric measures, logarithmic empiric measures. Again, we can pass to a limit, and it turns out that this limit is also a T-invariant measure. So we can speak about about measures which are visible but in a logarithmic way. So now what happens if we take these sets of, we consider these sets of visible measures, so it's either one measure, so in other words, a point is generic, or there must be uncountably many measures which are visible. And the reason for that is that this set is connected. Okay, and just going back to arithmetic functions, so if we have this U, just think that this is Möbius or Liouville, so then we can treat this point, this function as a point in the shift space, and then we can create a subshift, and we can ask ourselves what are the measures visible from that particular point. Okay, and this is the crucial notion which appears here, namely, given a sequence, so just think that this is Möbius. By a Furstenberg system of it, we mean the measure-theoretic system, where this measure, so this is just the subshift given by U, where the S is just the shift by one position to the left, and the measure kappa is visible from this point U. And we can define the logarithmic Furstenberg systems, well, in a similar manner. One thing we're talking about the entropy. Now we have topological entropy, and we know what is the entropy of measure-theoretic systems. But given a topological system, we have many invariant measures in general. So we can ask ourselves what are the entropies of these guys. So the variational principle tells us that the entropy of the measure is always small, is always dominated by the topological entropy. But on the other hand, we almost achieve, the topological entropy looking at the entropy of measures, invariant measures. In the case of subshifts, okay, so when A is finite, just notice that we have a very natural stationary process. Namely, the stationary, so we have the space A to the power Z, so we have the natural projections on coordinates. So once we have an invariant measure, we obtain a stationary process. So just please remember this notation, pi 0 on a sequence is just looking at the zero position. So in fact, if we have a subshift, and if we have an invariant measure, so the entropy of the whole automorphism is just given by this process. This is a separate theorem. Okay, so now let's go back to the Chowla conjecture. So what is Chowla conjecture from the ergodic theory point of view? Okay, so we want to see that all correlations of that type are equal to 0. So let's write these autocorrelations here in the following way, right? We look at these projections on coordinates. So these are continuous functions on the subshift determined by the Liouville function. And of course, when I look at these values, so it is nothing but the computation of the integral with respect to this empiric measure. So now the point is, what does that mean? What does that mean that all the limits which I have, they are equal to 0? When I look at these measures, these empiric measures, so these are measures which live on the space -1 to the power z. So I'm asking, okay, this is certainly going along a subsequence. From any subsequence, I can choose a further subsequence which converges. And I obtain a certain measure. But because of this claim of Chowla conjecture, the integral for this function must be equal to 0. But what are these functions? Well, these functions are continuous functions, and this is an algebra, and moreover, it separates points. So in fact, if I have a limit, and I know that all these integrals are equal to 0, there can be only one measure satisfying this property. What is this measure? Well, we are on that space. So obviously, if I take H measure of this group, it will satisfy this property because what I am considering here is nothing but characters of this group. So I know that this is in fact the Bernoulli measure 1/2 on that space. Okay, so from ergodic theory point of view, Chowla conjecture is nothing but the fact that lambda is generic for the Bernoulli measure. Okay. So assuming H1, right? So we assume Chowla. Okay. So let's write this Chowla, and so our aim is now to prove that we have Sarnak's conjecture, but instead of the Liouville function, we have, instead of Möbius function, we take Liouville function. So this expression, which we see here, we can write in this way. Now you see that this little x and the Liouville function, they are somehow symmetric, right? I have x, little x, which belongs to this deterministic system xt, and I have also Liouville, which belongs to a different system, namely Liouville function belongs to the Liouville subshift. But you see now that here is a continuous function, here is a continuous function. There is no reason not to see these two objects together. And this is what we do. We are considering now empiric measures, but on the two coordinates. So passing to a limit, let's pass to the limit, any limit, right, which we can obtain. So we obtain a measure rho, which is a T cross S invariant measure living on these two coordinates, x cross x Liouville. But this is not an arbitrary measure, which we can obtain in this way, because, well, we have two coordinates. If we forget about one coordinate, we have to see exactly the same condition, right? But the measure which we obtain will be the marginal of this rho. So because we assume that the Chowla conjecture holds, so what we see as the projection of rho on the coordinate given by the Liouville subshift, it must be the Bernoulli measure. On the other side, we don't know what we will obtain. This will be a certain invariant measure, but because the topological entropy is equal to 0, so the entropy of the limiting measure will also be equal to 0. And if we want to show that this limit is equal to 0, it's nothing but just to show that this integral is equal to 0. So you see that we end up with the following conclusion, that we have to show that the integral with respect to each rho, which I obtained in this way, of this function is equal to 0. So how to show that this is equal to 0? Okay. So in fact, what I'm going to show that if I have any joining between something which is of 0 entropy and the Bernoulli measure 1/2, so we want to show that in fact this integral is equal to 0. And it's enough to consider only the situation in which G takes finitely many values, because, well, we can approximate any function by a function which takes finitely many values, because we deal with a joining. And here is the crucial calculation. Okay, so on the side of the Liouville function, we have this process of projection of coordinates. So this is by our assumption, or I mean, we assume that Chowla holds, this process is an independent process. On the other side, it is this process. And what we know is that this process is a deterministic process, stationary process. So now let's look at this sequence of inequalities. So we compute the entropy of this independent process. So clearly, it is smaller than the entropy of this double process when we take I n and y n, which is given by the joining, because well, the entropy measures disorder, right? If I have pi and I have this process, so there is more disorder than pi. So the entropy has to be larger. Then we use subadditivity of the entropy, which gives us bound by the sum. But because this process has zero entropy, so then we find that this is h of pi. And finally, we end up that this is the same as the entropy of pi 0, because pi overline pi, not overline, but underline pi is an independent process. So in fact, we started with something, we ended with the same. So there are only equalities here. So then let's just write h of pi 0 is, as it follows, it's the entropy of this. And if you remember, we can compute the entropy of a process just by looking at the conditional entropy of the 0 variable with respect to the future. So okay, so we have this equality, and let's continue. So the entropy of this process is equal to this entropy, but the conditional entropy is also subadditive. So I can write that this is smaller than the entropy of the conditional entropies, the sum of conditional entropies. If we look at this guy, so of course, if I forget about these pi's here, the entropy can only increase. But if I forget about these pi's, I find nothing but the entropy of the process underline y. But this is equal to 0. So this is also equal to 0. And of course, the entropy here is smaller than the entropy of this variable. So again, we have equality. So what we obtain is that the entropy of this random variable pi 0 is nothing but the entropy of pi 0 with respect to the whole sigma algebra generated by 1, 2, etc. How is this possible? I mean, the conditional entropy is doing nothing. It's just we don't lose the entropy. Well, the only possibility is that pi 0 is independent of this. But if pi 0 is independent of the sigma algebra generated by these variables, so the more it's independent from the sigma algebra generated by y1, y2, etc. But why the sigma algebra generated by y1, y2, etc., it is everything, because our process is of zero entropy. So the past determines the future, the presence and the future, right? So everything. So in fact, it's the whole sigma algebra. So pi 0 is independent of the whole sigma algebra. And this gives us this condition. Okay, but we proved Sarnak's conjecture. So we proved Sarnak's conjecture, but I mean, we deduced Sarnak's conjecture from Chowla conjecture, but for the Liouville function. How to pass to the Möbius function? Well, we will use only this classical identity, relationship between Möbius function and Liouville function. And now let's notice that Sarnak's conjecture for Liouville function implies Sarnak's conjecture for mu. In fact, both conjectures are equivalent. How to prove it? Well, it's a simple calculation. So we want to show that this is going to 0. We apply this identity, and then we do the same with powers. We find this kind of expression, and we change the variables, and well, interchange the summation, and we find this kind of expression. So just look at this part and just think about d, which is small. If d is small, so then in fact I have t to the d squared, but this is an automorphism, right? So if t has zero entropy, powers, they also have zero entropy. So in fact, for these small powers here, I have something with zero entropy, and I assume that I know that Sarnak's conjecture holds for the Liouville function. So I know that these expressions are as small as I want. If only, I mean, I consider a bounded number of these. But of course, I mean, all these expressions are bounded by the norm of the function f, so they are all bounded. So the thing which really matters here is that the series 1 over d squared is summable. Okay, so we use Chowla for small powers, and then we conclude. I mean, if you want to see that these two conjectures, I mean, for mu or for Liouville are equivalent, so the other direction is just you use this kind of relationship. Okay, but this is okay. So this was the Sarnak's original motivation why we should study, why we should care about Sarnak's conjecture, right? So, of course, if we disprove Sarnak's conjecture, it means that Chowla conjecture does not hold. But this is of course not so obvious that, well, this can work, and it was a kind of a source of some controversies on, let's say, on dynamical side, because, well, suppose that we proved Sarnak's conjecture, so what? Okay, does it give us anything new for the Chowla conjecture? So remember, the Sarnak's conjecture was in 2010, and well, and then you can consider, well, to answer, I mean, all these controversies, or not controversies, but let's consider the logarithmic version of Sarnak's conjecture and the Chowla conjecture. So these are the same statements, but instead of Cesaro averaging, we use logarithmic way of averaging. So logarithmic Chowla conjecture, it's nothing but the fact that the Liouville function has only one logarithmic Furstenberg system, which is Bernoulli. We can repeat all this, in fact, all the proofs by just replacing Cesaro averages by logarithmic averages. And then, I mean, at least to me, it was a completely sensational result when Tao in 2016 he came and he showed that, in fact, on the logarithmic level, Chowla conjecture is the same as logarithmic Sarnak's conjecture. So these two things are completely equivalent. To see that, in fact, it gives us something about, if we try to reverse Sarnak implies Chowla. So let's consider the following observation. So suppose that we have a topological system and we have a point X. And then we look at measures which are visible from that point in the sense of Cesaro. And here we look at the measures which are visible from the point X, but in the logarithmic way of averaging. So in general, there are no relations between these two sets. And I mean, these two sets can be disjoint. And if you like, I mean, my favorite, let's say, multiplicative example is just to consider Furstenberg system for Archimedean characters, for functions of the form n is going to n to the power it. And then you will see that these sets, they can be equivalent. Okay, they can be disjoint. Okay, they can be disjoint, but not if you consider a convex envelope of this set. And this is a consequence of, of the summation by parts. If you look at logarithmic averages, so they are almost convex combinations of Cesaro averages. And when you pass to limits, so then in fact you conclude with this inclusion. So then the following lemma holds. So suppose now that on this left-hand side we have an ergodic measure. So what is an ergodic measure? Well, you remember that this was something like an extremal point, even in a larger space. So then what we are going to say, okay, so I said that these sets, they can be disjoint, but without this convex envelope, but not if on the left-hand side we have an ergodic measure. If we have an ergodic measure, then we claim that it has to come, it has to belong to the set of measures visible from the point X. Why is it so? Well, this is a very intuitive, this is a consequence of very intuitive theorem of Millman. So just imagine that you have a space and you have a certain subspace of that. I mean, when I'm talking about space, so just think about locally convex spaces. And then what you do, you just take the convex envelope of it. And you are asking, okay, what are extremal points of this convex envelope? And the answer is, okay, the only extremal points of this convex envelope, they have to come from this set you started with. And here we use this Millman result just to conclude, right? Because ergodic measures, these are extremal points. So of course, so this gives us, so let's see. So in fact, the Sarnak's conjecture implies the Chowla conjecture along a subsequence. Why is it so? Well, if we assume that Sarnak's conjecture holds, then of course logarithmic Sarnak's conjecture holds as well. But then we use Tao's theorem. Tao's theorem tells us, okay, but logarithmic Chowla conjecture holds. So it means that we have this equality, but the measure which we have, this Bernoulli measure, is ergodic. So by the lemma, this measure has to belong to the set of measures visible from the point from this function lambda, from the Liouville function. Of course, I mean, we obtain a result which is a little bit stronger than what we wanted to see, but well, anyway, this is of course not saying us what kind of subsequence we obtain, but Tao was able to obtain a stronger result, and he showed that in fact, the convergence takes place on a subsequence of full logarithmic density. Okay, so Philip, how much time do I have?
I would say about maybe 10 minutes.
Okay, 10 minutes. So because this is the first part, this was the first part of my talk, which is a kind of just showing, how ergodic theory proves this all relations. But of course, it does not. So we are still we don't advance, right? I mean, we would like to see. Okay, we have to prove one of these conjectures, Chowla conjecture or Sarnak's conjecture. Well, anyway, so I would like to show you. I mean, why this is so difficult. So here is a notion one can consider. So you remember we have this topological system, and we consider Sarnak's conjecture. Okay, so let's say, well, it's of zero entropy, and we can consider Sarnak's conjecture. But here I wrote something different, right? Also, we want to see that certain limit is equal to zero. But in Sarnak's conjecture, our claim is consider something pointwise, right? For all little point x. Here you see that something has changed because we consider uniformly, right? And it doesn't look correct even because, well, there is only one division here, 1 over bk. But if you divide this expression by bk plus 1 minus bk, so we divide here, then we have to multiply here and divide by this bk, which is common for all these little bk plus 1 minus bk. So then you obtain a convex combination, but you see that this is what we are going to compute is the uniform norm of certain averages. But they are somehow, we have intervals that change. There are small intervals, bk plus 1 minus bk, it's certain less, then maybe longer, then not necessarily longer, etc., because we want to see that this condition holds for all sequences such that the difference is going to infinity. So does it, I mean, when you look at that, it does not look very dynamical, this property, but wait a while. I mean, if we look at this supremum here, you can realize this supremum because all functions are continuous. So I can find points xk here so that I can realize the modulus of this function, right? And what we require is that this is equal to 0, but this is for particular xk. But if I take any xk, which is not realizing this supremum, I cannot get anything better than that. I have to obtain something which is smaller than that. But these are positive expressions here. So it means that in fact, for any choice of these points xk, I have to see that this limit is equal to 0. So of course, I mean, if I have this strong MOMO, so MOMO stands for Möbius orthogonality of moving orbits. And now you can see that, well, this is something what's happening here, because we are following orbits of different points. Well, anyway, this property implies Sarnak's conjecture uniformly. That's clear, but it looks stronger, if not much stronger, than orthogonality. Well, so I said that we consider orbits of different points. So what we do is the following, that we take this point x1, we follow its orbit, and then we change the point. We jump to an arbitrary point x2 and we follow its orbit, then we change, or we switch, etc., etc. And finally, what we obtain is a one-sided infinite sequence. Okay, and so it is natural to see this sequence as a member of two of one-sided subshift, but you see that this subshift has an enormous alphabet, because this space capital X can be already a subshift, for example. So the alphabet is enormous, but it's compact. So this space, I mean, this subshift it's a well-defined object. So the point is, what is this subshift? Okay, so I have to look at the closure of that orbit. So of course, in the closure, by definition, I see the orbit itself. But what are other points? Well, the other points, they're not so many new, because as you see, it is starting from U2, there is a place such that, in fact, from that place, I just follow the orbit of the point U2 in the space capital X. Maybe there is something, a finite piece of orbit of a different point. So if we forget about this part, just imagine the situation. I forget about this part. So what do we see here? So this is U2, TU2, T square U2, etc. But this is nothing different than as a space. This is nothing different as the space X. So the idea is that, okay, I started with a system T, I mean, with a homomorphism T acting on the space X, and somehow I added some new orbits, right? Some new orbits were added, and well, the point is, how big? I mean, is this new system really bigger than the original one, or not so much? Okay, so this reasoning shows not so much. Well, we will continue this in a while, but in fact, we have to repeat this construction, but with still a larger alphabet. We just add 3 points. Let's say roots of unity of degree 3, and we repeat exactly the same construction. We look at the subshift, and if we take a function which depends on the first coordinate, and here's its definition, so we multiply. So f is a continuous function on the space capital X. We multiply by the root of unity of degree 3, which we see on the first coordinate of this sequence A underline A, and we start making computation. What's happening? Okay, we want to see if Sarnak's conjecture holds or does not hold, so we want to see that this is going to 0. But when we develop what is coded here, so what we find is the following expression. Maybe let's jump here already. You see that, in fact, we have this kind of expression, but this is multiplied by this root of unity. So now if I choose this root of unity, so that all these expressions, okay, so they are, I don't change the modulus. So if I can multiply by a root of unity of degree 3, so that all the values, they will be in a convex cone of angle smaller than pi. So then, in fact, this expression is small if and only if I obtain that this expression is small. So this somehow explains the role of this strong Momo property. So anyway, we are interested in visible measures of this new subshift. And the analysis I showed you, it shows very quickly that in fact we cannot introduce entropy in this way. So in other words, all these new systems, they still have zero entropy. And if for example, if the system we started with had only one invariant measure, the new system which we obtain, the new systems which we obtain, they will all be of the same nature, and moreover, they will be isomorphic as measure-theoretic dynamical systems. Well, if you don't like this, and well, it's not so clear that you should like it because this is a dynamical point of view. So let's look to which condition it is equivalent. So, okay, so I suppose, so this is completely abstract. So we have let's say we have a Banach space, and we want to see that a certain sequence has this property, which we have seen a while ago, right? So we want to see that for all sequences, so that bk plus 1 minus bk, this is going to 0. And it turns out that this is equivalent to the following statement. And this is what in number theory is called, that in fact I'm interested, well, I have something which is of zero mean, but I'm interested in zero mean on short intervals. So what I have written here in this orange color, it is precisely the statement that we have that for typical short interval, the mean is also, well, going to 0. But in fact, this turns out to be equivalent to the statement that we have cancellations on disjoint short intervals. Anyway, so in particular, mu has, this Möbius function has cancellations on typical short interval if and only if it has cancellations on typical disjoint short interval. So was this property, I mean, was one of these experiments known in 2010? The answer is no. And in fact, the fact that for the Möbius function itself, we have this cancellation on typical short interval, well, this is only the theorem, this breakthrough theorem of Matomeki and Radziwiłł in 2015. So of course the result is quantitative, but in particular it gives this. Well, anyway, and here are some other, let's say, some other results. So first of all, it turns out that Sarnak's conjecture is perfectly equivalent to the fact that all zero entropy systems, they enjoy this strong Momo property. So in fact, we cannot avoid it. Right? This short interval business, well, it's as strong as Sarnak's conjecture itself. Another property, I mean, another difficulty, if you want to prove Sarnak's conjecture, is so a typical situation is that you take your favorite system and somehow you prove, okay, Sarnak's conjecture holds in this system. But now you know, but in fact, so let's take irrational rotation, right? For irrational rotations, we know that, well, Sarnak's conjecture holds. But there are many other systems, topological systems, which have exactly one invariant measure, and as measure-theoretic systems, they are isomorphic to irrational rotations. So are we going to prove in all these models, are we going to prove Sarnak's conjecture? Right? So you feel that, I mean, you can see that well, it's an infinite work, right? If in each model, to each model, you adapt a different method. So we are looking for theorems of the kind that if you have something for one model, then you have for all models. And this is a sample of results that if you have one model which has strong Momo property, then in fact you have for all of them. And I think I now jumped. So this is the last slide. So maybe I would like to present it slowly. So here is a theorem which we proved well relatively recently with Kanigowski, Kłaga, Przymus, and Delarue. which tells us that the following conditions are equivalent. So the first statement is that Sarnak's conjecture holds for all topological dynamical systems whose ergodic measures yield discrete spectrum automorphisms. Okay, ergodic measures only. So of course, discrete spectrum implies zero entropy. So if ergodic measures, they have zero entropy, so then from the variational principle, all measures, they have zero entropy. And so topological entropy is zero. So if you want to prove Sarnak's conjecture, you have to prove this, of course. And in fact, this is a very small subclass of zero entropy transformations. Okay, so let's think about this. So this is equivalent to the following fact that the second Gowers-Host-Kra norm of the Möbius function is equal to zero. So that's one statement. I mean, these two things are equivalent. Then the condition C tells us that if you take, well, the same assumption as before, ergodic measures yield discrete spectrum. So in fact, you have to see strong Momo property in all of them. So this is maybe not so surprising, but the D is very surprising because D is telling us take one system and show that it satisfies the strong Momo property. And look how simple this system is. So this is an algebraic unipotent automorphism of the two torus. Right? On the first coordinate, you see the identity acting. On the second coordinate, so you have these vertical circles, and you see that on these vertical circles, you have, well, rotation. If x is irrational, so it will be an irrational rotation. Right? So this is a very, very simple system. And if you think about Sarnak's conjectures, of course, this holds. I think that, well, Liu some years ago, 5 years ago almost, right? I think he showed you that, but in the paper by Sarnak and Liu, they dealt with general algebraic systems. And well, they proved that Sarnak's conjecture holds. But here we slightly, I mean, we change orbits, right? So we are in this one vertical circle, we follow an orbit, then we jump to another one, to another one, to another one. And it turns out that we are, well, we want to see that strong Momo property holds. So in fact, when you write this strong Momo property, so you find this expression. There are no points here because they are killed by the fact that we take absolute value, but you see what's happening, right? It's something which looks, I mean, you compare mu, this Liouville function, with irrational rotations, but the point is that the soup is here. And then because of the lemma I showed you, this condition is equivalent to this one. So this is again something on short intervals with the soup inside. So this is what Terence Tao calls local one Fourier uniformity, and these two conditions are equivalent. Well, so local one Fourier uniformity for the Möbius function is open. So in other words, we don't know whether, well, we know that the first norm, first Gowers-Host-Kra norm is equal to 0. This is by Mato-Meki-Radziwiłł's theorem. It's unknown whether the second norm is 0. It's just an open problem. So here is the main challenge now. I mean, how to prove this local Fourier uniformities. I think I stop here. Thank you for your attention.